Hello, today I'd like to present my findings on the neuromuscular junction. The neuromuscular junction is the synapse that connects the alpha motoneurons in your spinal cord to the muscles in your body. It is the final synapse out of your nervous system into your body to actually make your muscles move. Recently, scientists discovered the mechanisms that control how strong or weak this connection is. This synapse can get stronger with exercise, and it gets weaker in the absence of exercise. And so I'd like to present my findings on how this works. Let's start by defining what the neuromuscular junction is. The neuromuscular junction is the connection between the alpha motoneurons in your spinal cord, drawn here in purple, and the muscle, drawn here in red. And the neuromuscular junction is just a great big synapse that goes from the alpha motoneuron and it sits on the surface of the muscle strand. Now, it's a big synapse and there's some special properties about it. These synapses are set up when you're born, and there is one synapse on each muscle strand. The alpha motoneurons each connect to multiple muscle strands, but each strand of muscle is connected to by exactly one alpha motoneuron via a neuromuscular junction. So, to understand what this is doing in the context of the body, let's review what I discussed in the previous lecture about closed-loop control. The alpha motoneuron is a closed-loop controller. It tells the muscle to contract until the muscle reaches a set point, where the alpha motoneuron is commanded to go to a set point. And the muscle has proprioceptive sensors in it, which detect the amount of force in the muscle strands. Those are the Golgi tendon organs. And the Golgi tendon organs inhibit the alpha motoneurons in proportion to the amount of tension in the muscle. So the brain excites the alpha motoneurons in proportion to the amount of force that the brain wants the muscles to produce. And the muscles then, or the alpha motoneurons then excite the muscles until the muscles produce that amount of force as measured by the Golgi tendon organs, which then inhibit the alpha motoneuron. All right. Next up, I'd like to discuss the units that this closed-loop controller uses. Now, you might think that it's using units of force because it's controlling a muscle that produces force, but actually, the alpha motoneuron emits action potentials, which are little pulses of electricity that travel through the axon. It's how the brain, communicates. The Golgi tendon organ, likewise, is transmitting the amount of force that it's feeling using a series of action potentials. It basically comes down to the rate that it fires the action potentials at. The faster it fires action potentials, the more force it's feeling, or more force that the alpha motoneuron wants to produce. So we have a translation here at the neuromuscular junction between action potentials and force. There's a conversion happening between the electrical pulses and the force produced, and we can measure the amount of force produced per action potential. Now, the next thing to understand about action potentials is that there is a maximum frequency that neurons can emit them at. Neurons cannot emit action potentials faster than like a couple hundred hertz, because in between every two pulses of electricity, the neuron needs to recharge and prepare for the next pulse of electricity. So there is a maximum frequency that the alpha motoneuron wants to fire at, or is capable of firing at, and there is a conversion between each of those electrical pulses and the amount of force they produce, and this implies that there is a maximum amount of force that you can produce in your muscle. It's the amount of force that your alpha motor neuron can tell your muscle to produce. It's not necessarily the maximum amount of force that the muscle is capable of producing, but rather you could be limited by this closed loop controller being unable to command the muscle correctly. And on the other side of that coin, if this neuromuscular junction is too strong and it's converting between action potentials and force too vigorously, then a single action potential will create too much force, and your muscles will be like hyperactive, and you'll be unable to control the force precisely. You'll be like jittering your muscles. Okay, so the next thing I want to discuss is what the ideal strength of the neuromuscular junction is. Like, if we as engineers analyze this junction, what would we do? Well, what I would do is I would measure the maximum amount of force that you're ever going to want to produce. What is the maximum force in your whole lifetime that's going to have to come off of this muscle? And then I would measure the maximum activation frequency of the alpha motor neurons, which we understand the maximum activation. We understand that value because the limitation of activation frequencies from the alpha motor neuron is a biological limitation that is basically constant across all animals. So we take the ratio of the strength that we want to produce and the command that we're able to send to produce that strength, and it's just the ratio of those two things should be the neuromuscular junction's strength. However, we cannot know how much force we're going to want to produce in our lifetime off of the muscle. And what's more is there are different phases of our lives, and we might want to update the neuromuscular junction's strength. Every few years, things change. You grow up and you get stronger, and suddenly your neuromuscular junctions have to change in strength as well. So how does the body tune the neuromuscular junction? And I'm going to put forth the hypothesis that the body is analyzing the alpha motor neuron's activity, and it's looking for situations where the alpha motor neuron is asked to produce a higher frequency of action potentials than it wants to. And when the alpha motor neuron gets pushed too hard and it hits that limitation where it cannot produce more force because it's already hit the most force that it can signal to produce, that's when we strengthen the neuromuscular junction so that the alpha motor neuron can produce more force. I want to put out like a quick little reminder here that the amount of force that actually gets produced gets measured by the Golgi tendon organ, and there's a different system for making this work. So we will know how much force we're producing. That's not the issue. We can change the neuromuscular junction's strength, and the alpha motor neuron will get the message that its output is having more effect in the real world. So on the other side of Hebbian learning, if we're not strengthening the neuromuscular junction, we can also weaken the neuromuscular junction if the alpha motor neurons aren't getting pushed to their full potential. They're never getting pushed to activate nearly hard enough. Then we will weaken the neuromuscular junctions so that they produce less force out of the muscle. And this gives you better, more fine-grained control of the muscle because each action potential does less. And we only weaken it when we detect that we are not at risk of hitting the action potential limit. All right, and finally, let's talk about what the scientists have found that supports this hypothesis and that led me here. So, scientists found Hebbian learning happening at the neuromuscular junction. They found Hebbian learning, and they found the presence of NMDA receptors. Those are the molecules that are implicated and responsible for implementing Hebbian learning everywhere else in the brain. So Hebbian learning, what is it again? Hebbian learning is this idea that when the presynapse fires and it appears to cause the postsynapse to also activate, then we strengthen the synapse. We're looking for that correlation between presynaptic activity appears to cause the postsynapse to fire. There's a correlation there between the activity of these two things. We strengthen it. And if we do not detect that correlation, then we weaken the junction and eventually we'll remove the junction, because if the presynapse doesn't cause the postsynapse to fire, then we probably shouldn't be causing them to fire. At some point, we should just give up. And we prune it away. Now, not only do we prune them away at birth when we set up the connections to be, one neuromuscular junction per muscle strand, but those NMDA receptors are there throughout your life, and they appear to also help tune the strength of the neuromuscular junction, using this Hebbian learning mechanism. With the correct parameters of Hebbian learning, you could implement this hypothesis that I described, where the neuromuscular junction is looking for situations where the alpha motoneuron was pushed harder than it really wanted to be pushed, and it tunes the neuromuscular junction to keep its strength at sort of a critical point where it's almost not strong enough to push the muscle as hard as it needs to, but it is actually strong enough, because every time the alpha motoneuron goes into like a fit of hyperactivity because the muscle's not responding quick enough, then we strengthen it. That's entirely supported by the data, or entirely consistent with the data. However, this is not the explanation that they have provided. The scientists have merely found the presence of some form of Hebbian learning and the presence of NMDA receptors. That's not the same as saying my hypothesis is correct. It's still a hypothesis, although the evidence does not contradict it. Scientists have also found all sorts of other really interesting things about neuromuscular junctions. They've found that it takes about 2 weeks for them to learn. So if you spend 2 weeks in outer space floating around, then all of the muscles that keep your back upright, your posture muscles, those neuromuscular junctions will decay, because in space you don't need to hold your back upright. So those muscles were producing way more force than they needed to produce. And I imagine the astronauts had really hyperactive back muscles for a little while, and then they just sort of relaxed because their neuromuscular junction started producing less force. And then they get back down on Earth and the gravity pulls them down and they're all having, posture problems. But after about 2 weeks, the astronauts had recovered their muscles and their neuromuscular junctions had also recovered. They were able to measure this. When you do strength training and you're working out, it appears that for the first about 2 weeks of strength training, most of those gains are not actually the muscle getting stronger. It's simply the neuromuscular junction and alpha motoneurons getting better at exciting the muscle. But it's not necessarily that your muscle is getting stronger when you work out. I mean, eventually, if you work out enough, your muscle will get stronger, but often the early gains that people see when they first initially start strength training are due to this learning mechanism. All right, so in conclusion, I never expected to find this much interesting material to talk about the neuromuscular junction. Most scientists have kind of overlooked the neuromuscular junction because it's not really seen as learning anything interesting. But it turns out that it is actually learning a bunch of stuff. And it makes me wonder, where else in the brain is this same type of mechanism happening? The brain is full of closed-loop controllers. There are closed-loop controllers on the muscle force, but also on the velocity and position of the muscle. And there's a closed-loop controller on things like your body's posture and your vertical set point of how upright you are. Those are all closed-loop controllers, all the way up to there's a closed loop controller for your hunger level in your brainstem that controls your blood sugar. And when your blood sugar gets too low, it tells you that you're hungry and you need to eat. And then you eat, and then that satisfies the closed loop controller. Is that closed loop controller likewise using a similar type of learning mechanism on its output effectors? It makes me wonder. It makes me very curious to think about closed loop controllers in the brain. Anyways, I hope you've learned something interesting here. So until next time, meow.